I'm here to talk to you today about dynamic SIMS and how we use ion implants to be able to quantify data and some of the pitfalls that we can come across when we are using ion implants and how we quantify them initially. So, as Paula said, I work for Loughborough Surface Analysis. We are a contract analysis lab based in the UK, but do all sorts of work nationally and internationally as well. We specialise in dynamic SIMS, specifically the IMS-XF series from Kamika, in which we have 5 machines, 1 3F, 2 4Fs and a 7F auto, 2 7F autos, as well as many other parts of 3Fs and 4Fs that we're currently putting back together to build a 6th machine as well. The majority of the work we do is for the semiconductor industry, whether it be contamination or doping profiles and matrix profiles as well. But we also do other work such as R&D with universities, metal alloys, as well as other inorganic materials as well. Providing it can go in a vacuum and we can control the charge, we give it a good go at doing SIMS profiles on it. We also have the ability to do SEM, EDX, white light interferometry in-house and out-of-house. We can do XRF, EDX, various different surface analysis techniques to help complement SIMS analysis. So I'm first going to talk to you a little bit about time of flight and dynamic SIMS and how they differ. So both techniques use a primary ion source with time of flight, which is normally run in static SIMS mode. It's a pulsed primary ion beam, whereas with magnetic sector SIMS or dynamic SIMS, we use a continuous primary ion beam. These sources vary, so it tends to be cesium and oxygen sources for dynamic SIMS or magnetic sector SIMS. You can use these beams as well for static time of flight SIMS, but you also get molecular cluster beams, you get liquid metal beams, and they're currently developing water beams as well. So once you've selected your primary ion source, you then fire the primary ions at the sample. The sample is held at a voltage, be it positive or negative, and this voltage going across the sample creates an electric field which this is not going causes an electric field which extracts the secondary ions up the secondary column and into whatever sort of extraction you have on it. So for time of flight, we have a time of flight detector, which measures how long it takes the secondary ions to get from the sample through the reflector and back to the detector. With magnetic sector SIMS, we have an electrostatic extraction and a magnetic sector to separate out the masses before they get to the detector. With time of flight SIMS, we collect all of the masses at once. With it being pulsed, you send a pulse down and then you collect all of the secondary ions as it moves through the mass range. With magnetic sector SIMS, with the IMS series, we select the masses that we're interested in and we vary the magnet so that the masses are deflected into the detector, and we measure them in series so they cycle around the masses of interest. With nano SIMS, which is also magnetic sector, you can measure up to 7 masses simultaneously in 7 different detectors. So a couple of with dynamic SIMS, we also have an awful lot more lenses in place, or magnetic sector SIMS. So we've got several lenses down the primary column and the secondary column, which all need aligning to be able to get the secondary ions to the detector to be able to measure them. So comparing time of flight to dynamic SIMS. Time of flight is really good at spatial resolution across the surface, making it great for imaging. So you can get below a micron spatial resolution, which is great. And then we also have the detection limits of about parts per million. You can use this in dynamic mode, but we're not forming, it's still not a continuous ion beam onto the sample surface. So you're not forming an equilibrium region on the sample surface and forming a steady state. With dynamic magnetic sector SIMS, because we're using a continuous primary ion beam, we're forming a steady state on the surface. It gives us a much more accurate depth profile as we go through the surface, because you formed a steady state of whatever primary ion beam is being implanted into the surface. We get a much better detection limit. They're going down to parts per billion range, and can depth profile up to about 80 microns if necessary. Because the magnetic sector machines have been optimized for this depth profiling and this detection limits, we do lose spatial resolution. So we can image down to about a micron, but it's a toss-up between spatial and depth resolution. So you need to pick your type of SIMS depending on what you're interested in. Okay, so when we get samples, we have to select our conditions. So we can choose between our primary ion source and our secondary sample current. So if the elements that you're interested in tend to be on the right-hand side, we use a cesium primary ion beam and negative secondary polarity. And inversely, if it's on the left-hand side, we use oxygen primary ion beam and positive secondary polarity. This is a general case because SIMS is SIMS, there are always some exceptions. And we need to take into account other things, not just the ions of interest, but also sometimes what matrix elements are present, whether they will roughen under an oxygen primary beam or a cesium primary beam, and other possible interferences that might take place. And then a few anomalies. We've got the silver and gold, which prefer cesium negatives. So we would use conditions contrary to what you would expect based on where they are in the periodic table. And we've also found better sensitivity for zinc and magnesium using cesium and positive secondary polarity and monitoring the cesium polyatomics. So monitoring cesium magnesium instead of just magnesium gives us better detection limits than just measuring magnesium with oxygen secondary polarity. And then aluminium, if you have aluminium in your sample, it will enhance the ability of the other ions that surround it to ionize. So it's always something we have to take into consideration if there is aluminium in the sample and how that will affect the ionization capabilities, which is especially important in quantification, because if we don't consider the aluminium content, the ions of interest could be quantified. Okay. As said earlier, magnetic sector SIMS is great at imaging. It can do it, but what it's really good at is depth profiling. So a lot of what we do is ion implants of boron, phosphorus, arsenic, and silicon. Fairly standard for a semiconductor industry, getting a nice curve on the profile, and going down to background detection limits to be able to work out the dose of the implant. And then we can also do depth profiling of aluminium VCSEL structures. So you can see continuous depth resolution all the way down to about 40 microns at the surface, at the spike at the interface. And you can see all the different layers and how the aluminium content varies through each layer, which is really important to be able to make sure that the product does as it's meant to. and it's great for quality control. Okay. Iron implants. Most of what the analysis that we do, we want to be able to quantify it, to put numbers on the graphs rather than just an intensity scale. So LSA has a whole host of different implants of various elements in various semiconductor materials. And we run the appropriate reference alongside any of the data that we do. So we compare the matrix, so whether it be carbon or silicon or gallium arsenide, we pick the appropriate reference and run it under exactly the same conditions on the same day to be able to analyze. So here we've got a raw data depth profile with intensity signals on the y-axis and time on the x-axis. And with some equations and the relative sensitivity factor, we can quantify this data. So we can turn an intensity scale into an atoms per centimeter cubed scale. So the relative sensitivity factor is the ratio between the signal intensity of the matrix atom, so in this case carbon, and the nitrogen, which is the ion, the doping ion. And if we add these two equations together, we can compare a known sample with a known dose of, say, nitrogen with an unknown sample in the same matrix. So if this is a 1E15 dose, the area under this curve, or the integration of each of the individual points, is equal to a 1E15 dose. From this, in equation 2, we can get a relative sensitivity factor. So when we move to an unknown sample and use this relative sensitivity factor we got from the known dose, we can then convert the intensity scale into atoms per centimeter cubed. We would then be able to compare this quantified profile from day to day and from year to year. SIMS tends to have about 10% repeatability, which is incredibly good when you think about it, going down to like 1E17 atoms per centimeter cubed. Okay. So we've gone from raw data of a known sample with a 1E15 dose, which we're able to process, and then using the RSF from the processed implant, we can quantify an unknown sample to be able to get its dose. Okay. So another parameter that we're able to adjust on SIMS machines is our impact energy. So we can change the high voltage that goes across the ion source, with cesium normally being about 10 kV, and then oxygen, again, we can work at 10 kV, 15 kV. And then the sample high voltage, we can also vary whether it be positive or negative, or reducing it down from 8 to 5 to 3 kV. So depending on the different high voltages we use, and whether it's a monoatomic or whether you've got a molecule, you can work out the impact energy per atom that's hitting the sample. So if we use a 10 kV primary ion source and a negative sample voltage, we end up with an impact energy of 14.5 keV per cesium atom. And that produces this implant shape for the blue line here. We then lowered the impact energy, and you can see that at 9 kV, you get a much higher peak and a sharper diffusion curve as it comes down to the background levels. And then again, if you lower it further, you get an increased peak and a shallower diffusion profile. The area under these curves is all the same. They're all a 1E15 dose, but due to the impact energy, we can create different shapes of the profile. So when you're comparing doses over time, it's important to make sure you use the same impact energy if you're comparing the shape as well as the dosage. So it's just something to be aware of when you're getting iron implants analysed. Okay. Something to be aware of when you get irons implanted is possible contamination, whether that be from the implanter themselves not setting up the machine correctly, or possible external factors as well. So when we get a new iron implant, we ask for a specific mass unit to be implanted into the material. So in this case, we ask for 130 tellurium. And when we get it back, we run a mass spec. We make sure that we have only had 130 tellurium implanted. And you can see in this mass spec, we've got a big 1E4 peak at 130, and then 3 decades lower. 3 decades lower, we have peaks at 128 and half a decade lower at 122. So these are considerably smaller peaks, which is indicative of the entire dose being put into 130 tellurium. We can then run a depth profile with monitoring all of these different mass units or isotopes of tellurium, and we can see a nice Gaussian-shaped peak at 130 tellurium, a very small peak at 128 tellurium, which is very close to our background levels. It's only about 10 counts. And then nothing at 126 and the other minor isotopes of tellurium, which is perfect. It's exactly what we want to see when we get implants done. And we can use the equations for earlier to be able to quantify this. So we can convert the 130 tellurium into atoms per centimeter cubed, because we've got a depth on this as well. And we can then use this known sample of a 1E14 dose to quantify tellurium and indium phosphide in the future. We would then, if we got new implants, we would also, as well as going through this procedure of working out 1E15, we would also quantify with the old sample to confirm that the implanter has done their job, and then we have continuity between implants that we use for quantification. So this is what we get with a nice clean semiconductor. We've got some SIMS craters on the sample surface, but as we analyze them and over time, they sort of turn into this. So we get lots of pock marks on the surface as the sample degrades after being in and out of the vacuum and being exposed to air, possible moisture. And this can influence the depth profile that we get. And it's not something that we like to do. And so what we do is we get ourselves a present, which is a nice new iron implant of us in a semiconductor. And then we go through the same process. We run the mass spec. So this time we get 128 tellurium implanted. And what we can see here when we run the mass spec is not only do we have 128 implanted, we also have all of the other isotopes in considerable ratio. There's an awful lot of 126 and 130 tellurium in a supposedly pure 128 tellurium implant. And then when we run the depth profile monitoring these minor isotopes, we get implant shapes in all of the isotopes. And this is not particularly good. Because the peaks all line up, this is indicative of mass contamination from the implanter. and it's something we then have to take into consideration. So not only has the 1E14 dose gone into 128 tellurium, it's also been used to go into 126, 125, 130 tellurium. So we take this into consideration. So the area under all of these curves is equal to the 1E14 dose. So we then get for 128 tellurium, it's only a 7.86 E13 dose. This is quite a large difference in dosage, and we weren't particularly happy with this. But it's always a good way to check whether you've got mass contamination, especially if you're going to use the implant to quantify other samples in the future, because this can have a domino effect if you use the 1E14 dose rather than the 7.86 E13 dose. And here we've got each of the different isotopes quantified to show the varying doses for each of the different isotopes. Okay. Something that I noticed looking over the data was this extra little peak in here. So we've got a peak at 130.5 AMU. Just something to think about and maybe answer this at the end. What do you think this peak is? Because we're running a mass spec, it's always good to make sure we know what all the peaks are. Because if we've got an extra peak here, you begin to question whether it's part of this tellurium implant. We need to be able to identify it to be able to exclude it from our calculations. So have a little think about what that mass could be. Okay. And then the final thing that I'd like to talk about is energy contamination. So you can see we've got masses, all the different masses of selenium being monitored through this depth profile, but they don't have this nice Gaussian shape that you would expect of an ion implant. You've got some spikes in the gallium arsenide, and you've got much lower or much shallower peaks in both of them. So the peaks do not line up. This suggests that rather than being mass contamination, it's energy contamination when the ions have been implanted. There's not much research on why this energy contamination happens, but because the ion implants of the minor isotopes aren't at the same energy as the major isotopes, it doesn't influence the electrical properties of the semiconductor. So when we are doing ion implants for semiconductor work, we can exclude and disregard these energy contamination from the dosage. If anyone wants a fun little project, it would be great to see some more work on energy contamination of ion implants, because it would be nice to try and finally work out why this happens, and why it's different from different ion implanters. It's not consistent between different machines. But yeah, that's everything from me. So thank you for listening.